Okay, so let's go ahead and talk about the first type of chemical reaction. So the first type we're going to discuss we call combustion. So when you hear the word combustion, what pops into your mind is probably something burning. Okay. So most of the time that is actually the case. So if we see a word problem where it says write the balanced chemical equation for the burning of X, whatever it might be, then we want to write a combustion equation. Okay? So there are two types of combustion equations. The first one is by far the most common, so we'll look at it first. It's the combustion of a hydrocarbon. Okay? So the combustion of a hydrocarbon, so we have a general formula for it, looks like this. So we'll just say hydrocarbon. So that's something that contains only carbon and hydrogen. In this case it can contain oxygen as well, but we'll stick with carbon and hydrogen here, plus O2 gas yields CO2 gas plus H2O gas. Okay. So anytime we see a hydrocarbon plus O2 gas, these are our products. Those are just two products we have to memorize and know. So one little note here, this only applies to what we call the complete combustion of a hydrocarbon. So if we have enough oxygen and we don't run out of oxygen. If we do run out of oxygen, we produce a lot of other products like carbon and carbon dioxide. But for the sake of right now, we'll just assume that all combustion of hydrocarbon reactions produce these two products. Okay? So we said earlier that combustion was burning. Okay? So that's not a great definition though. A better definition for combustion is a rapid reaction with O2 gas. Okay, so we can also have something like a metal plus O2 gas. Okay, so this might not be burning in the traditional sense, and it is a very small sample of combustion reactions, but it is still technically combustion. But we'll often look at it in synthesis reactions. Okay, but for now, let's go ahead and look at the combustion of hydrocarbons. Let's get a few examples here. Okay, so I can say, let's see, the combustion of, we'll just say, ethane gas. Okay, so this requires a little bit of thought here. First, we have to decide what ethane gas is. So remember, F tells me two carbons. A and E tells me only carbon-carbon single bonds. Okay, so it's two carbons bonded together. Then we have to think, well, how many hydrogens do I have? Well, I know each carbon has 4 bonds. Okay, so I know that's the structure for ethane. So now I condense that down. So I have C2H6. The problem tells me it's a gas. And that's all I need to solve the problem, because I have the word combustion. Okay? Or you'll see the word term complete combustion. Or you can see the combustion of ethane gas in the presence of oxygen, which is kind of understood. Or you can see the burning of ethane gas. So a lot of different ways to word this type of reaction. So the reaction will look like this. C2H6 plus O2 gas yields CO2 gas plus H2O gas. Okay. So I'm on the right track, but I'm not done. So from this point forward, anytime we write a reaction, we have to go back and double check and make sure that it's balanced. Okay. So what I mean by balanced? How many carbons are on this side? 2. How many are on this side? Only 1. Okay. So I need to fix that. So go ahead and try this one on your own. It's best to do this in pencil. There's no magic process to balance reactions. It's kind of just a trial and error. If you try a number, it doesn't work. Okay, try another number, erase that and start over. I know in the past you've probably done the thing where you listed out carbon, hydrogen, oxygen on this side, carbon, hydrogen, oxygen on this side, and listed the numbers below. Hopefully in your academic career you're past that point and won't need to do that anymore. If you're still having to do that to balance reactions, the assignments will take you way too long to complete. So we need to practice this and get past the point of having to list out the atoms below each side of the reaction. Okay, so when you balance it, you wind up with these coefficients: a 2, a 7, a 4, and a 6. So if you're struggling to balance some of these in the first class of reactions, combustion, don't fret too much, just practice. Combustion reactions are by far the most difficult to balance, so it will get easier for you. So now when you're done, always go back and double check. Do I have the same number of carbons and hydrogen on each side? So then also go back and double check, can I reduce these coefficients? Okay, can I reduce 2, 7, 4, and 6? Hopefully you see, you cannot, so you know you're done there. Okay? So let's look at another reaction. Okay, so I might say the burning of benzene, and then I will tell you what benzene is, C6H6. We didn't, in case you didn't remember that from the common names that we learned. Okay, so burning, I assume that that's a combustion reaction with an excess of oxygen, so I assume it's going to be a complete combustion. Okay, so I'll go ahead and write it out. So I didn't say here, I can say the burning of liquid benzene. Benzene is typically liquid at room temperature. So whether the reactant that we combust is a gas or a liquid, it doesn't change the reaction really. So I have C6H6 liquid plus O2 gas. So don't forget oxygen is diatomic here, so it's always O2, yields CO2 gas plus H2O gas. So you probably know that combustion reactions release energy. Okay, so if you were to write plus energy as a product, you wouldn't be wrong here, that would be correct. But unless it specifically tells you energy is released or energy is absorbed, you won't have to worry about that for now. So now go ahead and pause the video, take a second and try to balance this equation. This one is a little bit trickier to balance, so go ahead and take some time and try to get through this one. Okay, so when you do balance it, you get 2, 15, 12, and 6 as your coefficients. So go back and double check and make sure you're correct. Make sure these can't reduce. Okay, so 2, 15, 12, and 6 can't reduce. So let me show you what I mean by reducing in case you're confused on that. So if you had gotten the coefficients to be 4, 30, 24, and 12, would that equation still technically be balanced? Yes, you would still have the correct number of atoms on each side, but you could go back and reduce all these numbers by 2. So you want to have the coefficients in the simplest terms possible. And also, one mistake to watch out for when you're balancing reactions and trying to reduce coefficients. Let's say I had this. I'm just going to make up a generic reaction. Let's say I had A plus B goes to C plus D, and I had a 2, a 2, and a 4. Could I reduce these coefficients? Hopefully you see that no, you can't, okay? Because even though there's no coefficient in front of C, we still know there is a 1 there, okay? So once you see the 1, you see you can't divide those by 2. So if it helps you to write the 1 in, I'm okay with you doing that. It's not necessary, but if you need to do that to help yourself out, you can. Okay, so those are the basic rules for writing combustion of hydrocarbon reactions. We'll go back later if we have more time and talk about incomplete combustion if we don't have enough oxygen, but for now let's just assume the products are going to be CO2 plus H2O. So now let's look at the combustion of a metal. Okay, so the combustion of magnesium is the one that we commonly experience. You can burn magnesium metal. It gets very, very hot very, very quickly. So if we talk about the combustion of solid magnesium, I'll have to write this reaction like this. Mg solid plus O2 gas yields. So hopefully you recognize Mg plus O2 cannot yield CO2 plus H2O. So those products only apply to the combustion of hydrocarbons. Okay? For this type of reaction, the combustion of a metal, we stick the two atoms together. So we write Mg and O. We just write them together and we write the correct ionic product. Okay, so you drop off the subscript, just write the two atoms. Now you have to go back and check your charges. So magnesium is plus 2, oxygen is minus 2. In ionic compounds, the charges always have to cancel. Do they cancel here? Yes, so I don't need to write subscripts, so I'm good. But now I need to go back and double check, is it balanced? Okay, no, it's not balanced. I have 2 oxygens over here, so I put a 2 right there, I put a 2 right there, now I'm balanced. Okay, so I don't have a symbol here for the phase of the product. In this case, you can leave that phase symbol off. We'll learn in situations in the future when we can predict the phase of a product, but for now, if it's not explicitly known or explicitly shown, like CO2 is a gas or it says liquid benzene, don't worry about the phase symbols for now. So let's look at one where these charges don't cancel right here and see what I do. So let's just say the combustion of solid potassium. So I have potassium solid plus O2 gas yields. Okay, so again, I just stick the two atoms together, K, O, but then I check the charges. Plus 2, minus 2, potassium's plus 1. So it's plus 1 minus 2 to plus 1 and minus 2 cancel. No, they don't, so you cross the charges and do K2O, and you leave the 1 off there. Okay? One important thing to note, be sure you always write the metal first. In ionic compounds, metals always are written first. So now go back and double check, make sure it's balanced. In this case, it is not. So I put a, you tell me, how do you balance this? This one's a little bit trickier. It's still fairly simple though. I need to make sure I have the same number of oxygens first. We'll go and look at that first, it doesn't matter where you start. So I have 2 oxygens here. I need to make 2 oxygens here. So now I have 4 potassiums over here. So I put 4 over here. Can I reduce 4 and 2? Well, I could, but there's still an understood 1 in front of that oxygen, so I can't reduce there. So the next type of chemical reaction that we'll discuss are synthesis reactions. It's where you stick 2 things together to make a new thing, and you'll see that the combustion of metals actually can fall into the synthesis category as well, but for now, because it is technically a combustion reaction, it is a rapid reaction with oxygen, we'll leave it here. Okay? So these are the basic rules for combustion reactions, predicting the products, balancing it. One thing I haven't discussed yet is we can write these reactions out in words. Okay, so for this reaction, for example, I could write in words 2 molecules of ethane react with 7 molecules of oxygen to produce 4 molecules of CO2 and 6 molecules of water. Or I could say 2 molecules of 2 molecules of gaseous ethane react with 7 molecules of oxygen gas to produce 4 molecules of CO2 gas, carbon dioxide gas, plus 6 molecules of water gas or water vapor there, okay? So just be aware if it asks you to write these out in words, it's just wanting to make sure that you remember how to convert from symbols to words to write the name. So don't be thrown off by that, it's absolutely nothing different.